Hello viewers, welcome to this video lecture series on analysis and design of algorithms. In this session I shall discuss the Warshall algorithm. Warshall algorithm is used to find the transitive closure of a directed graph. So I shall explain in detail with an example how to compute the transitive closure of a directed graph and what is a transitive closure. Floyd's algorithm is used to find the shortest path between every pair of vertices in the graph. Warshall's algorithm is used to find whether there exists a path between every pair of vertices. So in simple terms we can say Warshall's algorithm is used to find out whether there exists a path between every pair of vertices. So here we have written Warshall's algorithm is used for computing the transitive closure of a directed graph. Then what do you mean by transitive closure? The transitive closure of a directed graph with n vertices can be defined as n cross n Boolean matrix in which the elements in the ith row and jth column is 1. If there exists a non-trivial path, that is a direct path of a positive length from the ith vertex to the jth vertex, otherwise T of ij is 0. In simple terms, this transitive closure I can explain in this manner. Suppose if you have 4 vertices in a graph, you can represent the graph with a n by n Boolean matrix. So what do you mean by Boolean matrix? Boolean matrix is the values in the matrix will be either 0 or 1. So when it will be 0 and when it will be 1, suppose in case if there is a directed path existing between A to B, then it will be 1. So between A to D it is 1. Suppose if there is no path or directed path existing between A and A, it has to be written as 0. If there is no path or no directed path between A and C, then it has to be 0. So you will be filling the matrix elements either with 0 or with 1. This is the algorithm here for the Warshall. First 3 are the comment lines. You are going to implement the Warshall algorithm for computing the transitive closure, and the input for this algorithm should be an adjacency matrix A of a digraph with n vertices. The output will be the transitive closure of the graph, and these are the lines of code, that is, this is the pseudocode for this algorithm. I'll explain this pseudocode after I give you the complete explanation with an example. Then it will be more easier for you to understand this pseudocode. So let us take one example here. In this example, if you see, there are 4 vertices given and the graph is given here, a directed graph. You can see there is an edge here, okay, directed edge from A to B, there is a directed edge from A to D, and there is a directed edge from D to A. There is a directed edge from D to C. In the step 1, you need to find out the adjacency matrix. Adjacency matrices are not here, and the values for this adjacency matrix can be written by observing the graph here. So first we are going to see A to A, A to B, A to C, A to D. Then next B to A, B to C, B to B, B to C, B to, like this will complete writing the elements here in the matrix. The values will be either zeros or 1. Now look at the graph from vertex A to B. From vertex A to B you have a directed edge. So A to B I can write it as 1. Then from B to D, you have one directed edge. So B to D is here, I can write it as 1 here. From D you have 2 edges, one is to C and the other one is to A. So D to A is 1, D to A is 1 and D to C is 1. So out of the 16 elements present here, these 4 values are 1s, the remaining you need to write it as 0. This is called as the adjacency matrix or not. The next step is you need to come out with R1. Now how to compute R1? R1 to compute, first you write down all the vertices A, B, C, D, A, B, C, D. R1 matrix is computed by considering A as the intermediate vertex. So if you are considering A as the intermediate vertex from the adjacency matrix, that is from the previous matrix, whatever values are there for A, that means the first row and the first column, these elements you need to write down as it is: 0, 1, 0, 0, 0, 0, 1. And from the remaining elements, if you see there is one existing for B to D, so B to D1 you can write down as it is, and there is one more one appearing here between D to C, D to C1. So the remaining elements you need to check here. In this, the very first one is B to B. So R1 B to B, you have to refer R0. There you check the value for B to B, perform the logical OR operation, and from the previous matrix R0 you have to compute B comma A, logical ANDed with R0 A comma B. So here we need to find R1 B comma B, R1 B comma C, R1 C comma B, R1 C comma C, and for R1 C comma D, for R1 D comma B, and for R1 D comma D. These two are already ones. So one indicates what? That there is a path existing between B to D, there is a path existing between D to C. So only for us we have to find out these values, because all these values are 0 in the adjacency matrix. Now here we want to check, suppose if we use the intermediate vertex as A, whether any of the values which were earlier zeros here, whether it will get changed to 1. R1 first we are computing B comma B, R0 B comma B is 0, so you will write it here 0, or and R0, and from the previous matrix, so R0 is your previous matrix. B comma B, we are checking here B to A and then A to B. Via A, what is the via A, whether you have a path existing or not. Hope you are getting this point. In the matrix, in the adjacency matrix, B to B is 0. That means 0 indicates that there is no path existing between B to B. Now via A, whether there is a path existing or not, that you are going to find out in R1. So by introducing the intermediate vertex A. That's why we have written here B to A first time and then A to B. So we'll just check in the previous matrix what is the value for B to A. B to A is, B is here and A is here, it is 0, 0. Then logical ANDed with A to B. A to B is 1 in the previous matrix. So now when you perform this, 0 or 0 ANDed with 1 is 0, so you will get here 0 only. So finally what we have to do is, now we got B comma B as 0, so we'll write here B comma B is 0. We computed and we got it as 0. That next we need to find R1 B comma C. R1 B comma C, check in the previous matrix R0 B comma C, what is the value? R0 B comma A, intermediate vertex is A, logical ANDed with R0 A comma C. In R0, value for B comma C is 0. You can see here it is 0. Logical OR B comma A. B comma A is 0 and A comma C. A C is also 0. So in this case we got 0. So now we should write down here in the matrix is 0. The next one is 1, so no need to worry. The next is now C comma B we need to compute. So check the values here, R0 C comma B. In the adjacency matrix, what is the value for from C to B? C to B it is 0, logical OR. C to A, C to A it is 0, logical AND. Then A to B, A to B it is 1, 0 ANDed with 1 is 0 only, then 0 logical OR with 0 is 0. So for the matrix R1, C comma B is 0. Now next is C comma C. This one we need to compute. Now we'll substitute the values, check from the adjacency matrix what values are you getting. So we are getting here 0 itself. Next is this one, C comma D. So the value is 0. So we'll write here in R1, getting a value 0. Now we need to find two more elements here in R1. One is D comma B and another is D comma D. R1 D comma B. One ANDed with 1 is 1. So we are getting here 1. Then 0 or operation 0 or 1, you will get value 1. So now we are getting the value 1 here in this case. So we'll change this to 1. Now there is one more element left to compute, D comma D. D comma D. So we'll check what are the values. D comma D from the matrix D comma D, you can check here. D comma D, it is 0. Logical OR. D comma A. D comma A is 1. Logical AND. Then next you have A comma D. A comma D. A comma D is 0. 0 logical OR. Compute first this. 1 ANDed with 0 is 0. So you will get 0. So D comma D in R1 is 0. Earlier D to B in the adjacency matrix was 0. Now we got a value 1 via the intermediate vertex A. So once we compute R1, now we should compute R2. To compute R2, you are taking B as the intermediate vertex. So when you take B as the intermediate vertex, whatever are the elements pertaining to B, that means the second column of R1 and the second row of R1 pertaining to B, those values you should not disturb, keep it as it is in R2. So these things you have to keep it as it is, and then you need to compute the remaining. So use the same way how I have computed for R1. So now you have to compute for R2, and R2 if you check here, first is A comma A, so you will be writing A comma A, but for you the reference matrix now will be the previous one is R1, so you will be taking R1 A comma A, logical OR R1. Now intermediate vertex is B, so A comma B ANDed with, you are doing for A to A, so A to A is what? You are introducing the intermediate vertex as B, A to B and then B to A. So A to B, R1, B to A. Now compute the value in the same way R1. That means now you are referring what? The matrix R1. In R1, A to A. A to A is here, A to A is 0. So you will write here 0 OR operation. Then in R1, A to B. A to B. A to B in R1 is 1. 1. Logical ANDed with. And in R1, B to A. B to A. B to A is how much? 0. So 0 you will write here. Then you will write 0 or first compute this. 1 ANDed with 0 is 0. 0 or with 0 is 0. So now you have to write down for A to A in R2. That means this value when you computed you got 0. So you will write it here 0. So this way you need to compute now A to C, A to D, then C to A, C to C, C to D, D to A, D to C and D to D. So same procedure you follow and fill the values for R2. Once you calculate R2, then you need to compute R3, and when you are computing R3, you are taking the intermediate vertex as C. After that you compute R4, in that you take the intermediate vertex as D. Calculate the values by using these formulas. I'll write down here directly what are the elements that are there in R2, R3 and R4. So for R2 the values are, now I'll write down the values for R3. For R3 you are taking C as the intermediate vertex. So when you are taking C as the intermediate vertex, what you have to do is from the previous matrix R2, whatever are the elements pertaining to C, that column and that row elements you have to note down as it is in R3 pertaining to C. this 0 0 and this one pertaining to C, this column and this row. If you observe here, we have copied down as it is 0 0 1 and 0 0 0, and the remaining elements we have computed by using the formula as we have done in the previous matrix. Now you have to compute R4, and so this R4 you have created by taking D as the intermediate vertex. When you started calculating the values for R4, one row and one column pertaining to D from the previous matrix you have to copy down as it is. So which one is that? This column and this row. Okay, these elements you have to copy down as it is, and then the remaining elements or whichever are there, these elements you would have got after substituting in that formula. So final matrix what you got is R4 in this case. See, we covered all the vertices here. We created R1 with intermediate vertex A, we created R2 with intermediate vertex B, we created R3 with intermediate vertex C, we created R4 with intermediate vertex D. And whenever we created the matrix R1, for us the reference matrix was R0. Whenever we created R2, for us the reference matrix was R1. When we created R3, the reference matrix is R2. When we created R4, the reference matrix is R3. That it is always the previous matrix. So if it is 1, 1 minus 1, 0. The current matrix is K, then the previous matrix will be K minus 1. That is how is the formula given here. If you observe the formula which I have written here initially in the problem statement, RK, K is denoting your current matrix, K minus 1 is denoting your what? The previous matrix. So I comma J is for that particular row and column element. Okay, for that particular row and column IJ, you are introducing the intermediate vertex. K here is your intermediate vertex. So this way you have computed every time. If you remember, for the R1 you have taken always intermediate vertex as A for all the elements. Similarly, when you created the this matrix R2, you have to use B as the intermediate vertex. Then when you created R3, you have to use C as the intermediate vertex. When you created R4, you have to use D as the intermediate vertex. Now finally we got R4. R4 is what? Our final matrix. So now you just see the pseudocode, then it will be more clear to you. The very first line says, see, R0 is the adjacency matrix, this one which we created. Find the very first one just by observing the graph. R0 is what? The adjacency matrix. Then for K 1 to N, for I 1 to N, for J 1 to N. So these three for loops we are using here. For K 1 to N, because K is the intermediate vertex, we have to cover all the intermediate vertices. Here N is equal to 4. We have 4 vertices in the given graph. So in our example, N equal to 4, because we have 4 vertices in the given graph A, B, C, D. So K value 1 to N, we have considered the intermediate vertex. First time A, second time B, third time C, and fourth time D. So every time for every intermediate vertex, for I equal to 1 and for J equal to 1, whatever are the elements you need to compute, you are using this formula. Okay, this one. So that is how you can see one for loop within the other for loop. 3 for loops are here. One for the intermediate vertex, one for the row, and another for the column. And you are computing using this formula. RK. K is your current matrix calculation. K minus 1 is you're referring the previous matrix. And finally the last statement is return Rn. N here is 4. So whatever we computed the last matrix, what we got R4 is your final matrix. Now just compare the final matrix with the first matrix what you got. R4 is here we have computed. I'll just write once again here the adjacency matrix what we had written initially. Now after doing all the computations for all the different matrices, the final matrix what we got is R4. And in R4, if you observe, these are the values. Initially if you see, there were only just 1, 2, 3 times the 1 was appearing. Now how many times the 1 is appearing? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times the 1 is appearing. That means what? Initially there was a path existing between only these vertices, whichever are shown as 1. Later we found that via intermediate vertices also we can reach the other vertices, and we could see the paths existing between these pairs. So 1 1 in the final matrix indicates now that there is a path existing. A to A there is a path existing, A to B there is a path existing, A to C path existing, D, B here, B to D. Then now only C to A, C to B, C to C and C to D there is no path existing, whereas once again D to A, D to B, D to C and D to D there is a path existing. So you can always cross verify once again with the graph which was initially given in the question. Now you can check A to A is 1 in our final matrix. Because there is a path existing, yes, A to A you can travel via B. A to B first, B to D and then D to A. A to B, here there is A to C. A to C also there is a path, A to B, B to D and D to C. Then A to D, A to B first and B to D. Then B to A it is shown 1 here, B to A. So it will start from B to D, then D to A. So it is like B to A. B to B there is 1. B to B, yes, it will start from B to D, D to A and then A to B. B to C, B to D and D to C. B to D also there is a path existing. Now here if you observe in the final matrix, C to A there is no path, yes, even from the graph we can make out there is no path. C to B there is no path, C to C there is no path, C to D also there is. D to A whether we have a path, yes, we have a direct edge D to A. D to B we can travel via A, D to A and then A to B. D to C is 1 here, D to C we have a direct edge. Now D to D is 1. So D to D is 1 means D to A first, then A to B, then B to D. So this way whatever was the adjacency matrix we wrote from the given graph, we could finally write what? The transitive closure. Now R4 what we got at the end of this solution is the transitive closure of the given directed graph. So this is how you need to compute the values. The time efficiency for this algorithm is theta of n cube. We got the time efficiency for this algorithm as theta of n cube because the basic operation rk I comma j, this line, okay, this is the basic operation which is getting computed. This basic operation is getting computed for every value of all the 3 for loops k, I and j. So n into n cube. So that is how the time efficiency for this algorithm is theta of n cube. Hope you find this session helpful. Please like, share and subscribe to my channel. Thank you. Bye bye and take care.